Can you hear me? Audio is clear to everyone.
Yes, sir.
How are you? তোমরা সবাই কেমন আছো? ওয়ালাইকুম আসসালাম।
আসসালামু আলাইকুম স্যার।
হ্যাঁ, ওয়ালাইকুম আসসালাম। তোমরা সবাই ভালো আছো?
এই তো স্যার ভালো। আপনার কি অবস্থা?
আমি ভালো আছি।
নমস্কার স্যার।
নমস্কার। Okay, we will start after 1 or few minutes. তোমাদের অনলাইন লেসন গুলোর অগ্রগতি কেমন? প্রগ্রেস কেমন? ইজ গোয়িং ওয়েল? তোমাদের কি?
ভালোই স্যার মোটামুটি।
ওকে। তোমরা তো মনে হয় ইন প্রেজেন্স ক্লাস করো নাই, তাই না? You just started second year with online lessons.
কয়েকটা করা হয়েছিল স্যার।
আচ্ছা, কয়টা ক্লাস হয়েছিল? ওকে।
শুরুর দিকে ওটা।
আচ্ছা, তোমাদের কি মাইনর ক্লাস আছে নাকি অনেক সেকেন্ড ইয়ারে? ফিজিক্স?
আমাদের মেজর কোর্স স্যার 3টা আছে মোট। সিপিটি, এনভায়রনমেন্টাল আর ফিজিক্যাল কেমিস্ট্রি। আর সবগুলো মাইনর।
Okay, so okay, fine. So still you are not a student of applied chemistry. কারণ ফার্স্ট ইয়ারও তো অনেক মাইনর কোর্স, সেকেন্ড ইয়ার অনেক মাইনর কোর্স। রিলেটিভলি মেজর কোর্স থেকে মাইনর কোর্স অনেক বেশি। Today we will start redox processes in aquatic environment. Okay, এখানে কিছু ক্যালকুলেশন থাকবে, তোমরা তোমাদের নোটবুক রাখতে পারো, because it's oxidation, reduction, reaction and so on. তোমরা এটা নোটও রাখতে পারো, কিছু কিছু ক্যালকুলেশন থাকবে, ইকুয়েশন থাকবে and so on. Okay, well, again, good evening to everyone. We can start now. Maybe I can use the annotate. Here it is. Okay, fine. Here in the last lesson, actually, we talk about the reactions. Different reactions in aquatic environment. We talk about the acid-base reaction and so on. Another important class of reaction is the complexation and chelation. I think you already know something about that. Complexation means is actually making formation of a complex in presence of some metal ion, some ligand, making complex formation. As you can see here, there is actually complex formation. This is here you can find, and this is actually important. In different cases for metal ion sorptions or precipitations or solubility or insolubility, this is actually important. Here you can find a chelating agent actually has more than one atom that may be bonded to a central metal ion at one time to form a ring structure. Okay, here you can see the pyrophosphate ion. Here you can see pyrophosphate ion. Okay, it's a chelating agent. It can bond to the calcium ion. Okay, to form the this chelate. Okay, this is like complex. coordination bond, complexation bond. Okay, it sometimes the metal ion is called a complex ion or coordination component and so on. Well, fine. Here you can see some ligands. The ligands found in natural waters and wastewater contain a variety of functional groups, which can donate electrons required to bond the ligand to a metal ion. Among the most common of these groups are carboxylate, heterocyclic nitrogens, phenoxide, aliphatic and aromatic amine, phosphate, and so on. These ligands complex most metal ions found in unpolluted waters and biological system, magnesium ion, calcium, manganese, iron, and so on. So this cleared, these ligands complex, they form the complex with the metal ion. So you can see also here complexation form. Okay, just give an idea. Complexation is also important for have a quality of the species present in the aquatic environment. Complexation may have a number of effects, including reaction of both ligands and metals. Among the ligand reactions are oxidation reduction, decarboxylation, hydrolysis, and biodegradation. The formation of insoluble complex compounds remove metal ions from solutions. Complexation may strongly influence metals absorption, distribution, and fate, as well as biochemical effects, including bioavailability, toxicity, and plant uptake. I think you already know this. Complexation from these heavy metal ions and so on. Okay, is also important for water treatment plant. Okay, so removing the heavy metal ions from the wastewater and so on. Complexation. You study in details of the in water treatment plant and so on, or polywater effluent treatment plant and so on, how to remove the heavy metal ion by forming complex bond. Okay, okay, this is just give an idea, but our main focus is the redox reaction because our chapter is redox processes in aquatic environment. So before going that detail, we just need to remember, just give an idea what is oxidation and reduction reaction and so on. Already you know all this stuff. It's just for a memorization, just for like a recap. Okay. Here you can see redox, a chemical reaction in which one component loses electrons or is oxidized and another gains electrons or is reduced. Okay, so that means the component, okay, which loses electrons is oxidized, and the one which gain electrons is called the reduced state. And this uh, gaining and losing electron take place in a simple in a reaction, in same reactions. Okay. Definition of oxidation, I think you know all this, is addition of oxygen, a chemical reaction in which oxygen or electronegative group is added to an element or compound is called the oxidation reaction. Loss of electrons, the process of losing electrons from a chemical element or compound is called oxidation. It's just definition, I think you know this thing. Also, reduction is just opposite of oxidation, a chemical reaction that brings about a gain in hydrogens or loss in oxygen or an increase in electron. Okay, it's called the reduction. It just gives an idea. So the important thing is in particularly the definition of electrons. Loss of electrons is known as oxidation, and gain in electrons is reduction. Okay. Well, fine. Here in redox, because it's a combination of redox and oxidation reaction, we can have a half reaction. I think you know this, half reaction. A half reaction is either the oxidation or reduction reaction component of a redox reaction. That means redox reaction is a combination of oxidation and reduction reactions. So if we consider this reaction, here you can see reduction of iron 3 ion to iron 2 ion. So the overall reaction we can represent this way. Okay, in this reaction is actually presented in double arrow. That means it's a reversible reactions. As the reaction goes to the right way, that means this way. Okay, right way. The hydrogen is oxidized as it changes its oxidation number of 0 to higher oxidation number of +1. Okay, if we consider the reaction, you can see this is a reversible reaction. If the reaction go right way, that means this hydrogen is oxidized. Okay, that means is oxidized mean is actually reduced, is release electron. And by doing this, its oxidation number here in elemental hydrogen oxidation number is 0. But here you can see this oxidation number is +1. That means oxidation number increased. Okay. So the even in case of iron, you can see the oxidation state of iron goes from +3 to +2. Okay. So the oxidation number of iron decreases. That means that this is iron is reduced. This means it's reduced. Well, here, so here actually it's hello. Oh, sorry, there was interruption. Can you hear me? Hello.
Yes, sir.
Yes, sir.
Okay. Okay. Sorry for that. There was interruption. Okay, we can proceed. Here in this reaction, you can see this reaction. There is actually this redox reaction. We can divide. We can broken down into a reduction half reaction. In this case, this one iron 3 ion reduced here. You can see iron 2. So here iron 3 plus ion is accept 2 electron. Okay, gain in electron. Huh? So gain in electrons is the reduction. It's called reduction. So this is the reduction half reaction. Okay. And oxidation half reaction is the hydrogen. You can see elemental hydrogen is released. It loses electrons and it forms a hydrogen ion. Okay. So this is you can see the oxidation reaction because loss of electrons happen here. So this one is called the oxidation half reaction. So if we add these two reactions, then we call okay, reduction half reaction plus oxidation half reaction, then we can this one, redox reaction. I think you know already this stuff. You studied a lot about this in first year or even in the intermediate stage. Okay. Well, fine. It just haven't given ideas like a recap of intermediate lessons. Here, the significance of redox reaction in environment. This is very important. What is the significance? Why should we study redox reactions in environmental chemistry? The first one, redox reactions are very important in natural water system. In fact, all aquatic organisms obtain their energy for metabolic processes from redox reactions. Okay, this means metabolic process in metabolic reactions, redox reaction is happen. Suppose if we consider in our case human body, we know the metabolic process, the mitochondria. In that case, we have this mitochondria. This metabolic process happen, and redox is a very important step. Okay, photosynthetic organism catalytically reduce carbon dioxide to reduce organic matter by trapping light energy, while non-photosynthetic organism catalytically decompose the organic products of photosynthesis to energy yielding redox reaction. I think you already know this thing, photosynthesis reaction. Here actually this is also a redox reaction as well as the degradation. Degradation of the biomass is also a redox reaction. And both of these have a significance in the existence of human life in this universe. As you know, by photosynthesis reaction, the atmospheric oxygen level is maintained. We know that in our environment here, we have 21, around 21% is oxygen. So photosynthesis maintains also this atmospheric oxygens. Okay, this level, constant level, nearly constant level. Another one is the nitrogen. Nitrogen, which is one of the major elements in the terrestrial and aquatic environment, circulates by many microbially catalyzed redox reaction. Okay, that means in nitrogen cycle, redox reaction play a significant role. And the number four, the movements of many other elements also involve redox reactions such as carbon, iron, and sulfur. Okay, so you can see the importance of redox reactions. Number five, life is powered by redox reaction. This is very important. Life is powered by redox reaction, chemical processes in which electrons are transferred from one molecule to another with the release of energy. Organisms have evolved machinery made up of proteins and membranes, which channels this energy into the biochemical pathways that support vital functions. Okay, it just you can search this stuff. The importance, significance of redox reactions in life, maintaining life. Okay. In an aerobic environment, the most important biological redox process is actually degradation of hydrocarbon. You can see here it's happen. Yeah, oxygen. We could have carbon dioxide and water, a smaller molecule. Because this is a high molecule hydrocarbon is actually degraded, fragmented into carbon dioxide and water. And the final one is contribution to aerobic art. Okay. What does it mean? Contribution to aerobic art. Because you know that in atmosphere we have, as I told, that 21% by volume is oxygen. And here, how could it come here, 21% oxygen? If you study the evolution of Earth, you can find it. As a scientific theory, we know that Earth actually it started its journey around 4.6 with around 1.5 billion years ago. But at the initial state, the aerobic oxygen, what we call it now, is a 21%. It was not like that percentage. If we consider 2 billion years ago, the atmospheric oxygen level was around 1%. Okay, but now it become 21% and it remain constant. And this is vital for the survival of life of human being in this planet. Because you know that if oxygen level if increases too much, then the metabolic process and respiration will be higher, and it will be destructive for the survival. And there is a feedback system also. Feedback system, that means 21% oxygen level is remain constant around 450 million years. তো 450 মিলিয়ন ইয়ার্স ধরে আমাদের যে আর্থের যে অ্যাটমসফিয়ার যে অক্সিজেন লেভেল সেটা এখনো কনস্ট্যান্ট আছে। দ্যাট মিনস সামওয়ান ইজ প্রডিউসিং দ্য রেট অফ প্রোডাকশন অফ অক্সিজেন equal to the rate of decompose, sinking of rate of production and rate of decaying oxygen is same equal. Okay, there is equilibrium process, and in this case redox reaction play a significant role. If you study the evolution of life or evolution of atmospheric oxygen in the earth, you can find more details about the redox reaction. Due to the shortage of time, I just given one sentence: contribution to aerobic earth. Well, fine. Here, redox potential. The redox potential is a measure of the affinity of a substance for electrons compared with hydrogen. Okay, I think you know this redox potential is like a relative affinity of a substance for electrons. You also know the is colors in electronegativity. Okay, compared to the hydrogen, which is set at 0. Substances more strongly electronegative than hydrogen have positive redox potential. In this table, you can see redox potential. So this is actually hydrogen redox. You can see here. Redox potential of hydrogen is 0. Is set up is a convention is taken as 0. Okay. Substances more strongly electronegative than hydrogen have positive redox potential. Okay, but substances less electronegative than hydrogen have negative. Here you can see cation have negative redox potential. So from this redox potential, we can have an idea the relativeness, relatively the attractiveness towards an electrons by an substance. Here we will see electron activity and PE. This is very important for redox reactions. PE. Okay, we can define P as the negative log of the electron activity in the solution. It's a definition of P. You can say P equal to minus log, negative log of the electron activity in the solutions. And this P is analogous to the PS definition. Okay, you can see PS equal to minus, you can say equal to minus log of hydrogen ion activity in the solutions. It is very similar. PS indicate the activity of hydrogen ion in the solutions, but P indicate the electron activity in the solutions. Okay, what does it mean actually electron activity? What does we mean electron activity? And because I think you know that hydrogen ion concentration, but concentration is not the real term. Okay, it doesn't have any meaning. It's actually hydrogen ion activity. Activity has the meaning. Okay, here you can say what does it means electron activity. Electron activity is the expression of ability of electrons in the solutions. Okay, electron activity means ability of electrons. So ability of electrons to an electron accepting substance in the solutions. Electron accepting substance, you know that actually electron accepting substance that means a substance who have affinity to accept towards accepting electron. Okay, so electron activity means the ability of electrons in the solution. This is important, availability of electrons. Here in this you can see the actually resemblance of P to PEs. Okay, here I just read this one because it's very important. You have to know this thing. Here, the activity of the hydrogen ion is used to express the extent to which water is acidic or basic. Okay, here pH. From the pH value, we know that whether the water or the solution is acidic or basic. I think you know this. pH equal to 7, then we call it the neutral. If pH lesser than 7, then we call it acidic media. If pH greater than 7, we call it the basic media. Okay. The activity of the electron is used. So here activity of electron is used to express the degree to which an aquatic medium is oxidizing or reducing. So activity of electron means whether media is oxidizing or reducing. Okay, and hydrogen ion activity actually indicate whether a media is acidic or basic. It's analogous. Okay, just have an similarity. Huh? Water with a high hydrogen ion activity, such as runoff from acid rain, is acidic. You know that acid rain or something. If the hydrogen activity is high, that means it's acidic. By analogy, water with a high electron activity, such as that in case of anophysis digester of a sewage treatment plant, is said to be reducing. Okay, high electron activity means is it reducing environment. Again, I am saying high electron activity means this media is a reducing environment. Water with a low hydrogen ion activity, that means low hydrogen ion activity, that means higher concentration of hydroxyl ion. Okay, you know that. Such as landfill is at contaminated waste or so on. It's a basic. Okay, if in the water hydrogen ion activity is low, then we call this is a basic. This water is basic. Whereas water with a low electron activity, okay, is said to be oxidizing, such as chlorinated water. Okay, that means chlorinated water is oxidizing. Okay, oxidizing means here electron activity is low, and reducing media means electron activity is high. It just give an idea, analogy. Okay, what does it mean? It's very similar, P and pH. Okay, actually neither free electrons nor free hydrogen ions as are found dissolved in aquatic solution. You know that neither free electrons nor hydrogen ions freely present in aquatic solution. They are always strongly associated with solvent or solute species. However, the concept of electron activity, like that of hydrogen ion activity, remains a very useful one to use in the aquatic environment. Okay. So this is very important. This PE here you can see the electron activity of electron. Okay, here electron activity is the negative log of the electron activity in the solutions, but PS is the negative log of the hydrogen ion activity in the solutions. Well, and if you have any questions, you can ask me later because it's very important. We have to go also derive some equation regarding P. What does this means? Reducing environment or oxidizing environment? You have to know this thing. Here, you can see aquatic environment. This one you can see is a stratified body of water which has a high oxygen concentration. Here, upper layer, uh, near the surface, it has a high oxygen concentration. Means high oxygen concentration means high P value and oxidizing near the surface, and a low oxygen concentration near the bottom. Here you can see, here is atmospheric oxygen X7. Here you can see all oxygen is available here, high oxygen in oxidizing media. But in reducing, it is very low oxygen is available. Okay, but metal ion, you can see metal ion presence here. It's a free metal ions you can see. I don't do and this present here. Okay. And this is the also hydrogen sulfide. This is a gas, methane gas. You know, this methane gas all found in the bottom, bottom of the stratified regions under the oceans and so on. You can see here, and here you can see oxygen. High oxygen concentration. Here is a low oxygen concentration. Okay. So that means that here high oxygen concentration means the oxidizing media, and here PE value is high PE value, and the bottom low oxygen concentration. That means a reducing environment, reducing media, and low pH value. Sorry, PE value. Here now we will try to derive the PE equation. Here I can write a half reaction oxidized. You can see there is a reaction oxidized, and this and electrons and numbers and moles of electrons and is reduced. Okay, this is a reaction. Okay, in which OX and R is a red ox and X represent upper and lower oxidation state of a redox pair. Okay, OX is a upper oxidation state such as iron 3 plus, and this is of course the lower oxidation state because it's accepting electron. Okay, so here we can write the equilibrium constant. I think you know this thing, equilibrium constant K equal to, here we can see redox concentration of here redox and then activity of oxidized species and then electron here, electron activity here. It's just like I think you know in the equilibrium equation thermodynamics you studied this stuff. Okay, in this equation, you can see the electron appears explicitly. Here, electrons. Okay, these electrons, and the number of moles is go to the power. Okay, although the electron has no independent existence in aqueous solution, its activity, which is a direct measure of its free energy, represents a very real quantity. Hmm. So here you can see activity is important because it is present the real quantity, the availability of electrons in the solutions. Okay, activity. Thus, the concentration term, you can see concentration, this is the concentration term, would have no physical meaning. Okay, concentration term has no physical meaning. Only the activity term or availability of electrons has the physical meaning. But the activity is an expression of the availability of electrons in the solution, and thus of its reducing power. Okay. This is exactly analogous to the way in which the hydrogen ion activity expresses the ability of the solution to supply protons to a base. It's just analogy as I talked earlier. Okay, because hydrogen ion activity means the ability of the solution to supply protons to a base. So we can solve the Vogel equation for this activity of electron. Here we can rearrange this one this way. Okay. And here we from this equation we come here actually. I think you know this thing is your homework. How could we come from here to here this equation? This to this, I think it's very simple. If you take log in both sided and then you can simplify this one, you could have this type of equation. Okay. Here P equal to 1 by n log K minus log of reduced state divided by oxidized state. And if we consider this one as a Q is called the reaction quotient, okay, Q, we can make it simplified way. P equal to 1 by n log K minus log Q. So Q equal to this one, okay. Okay, you will try to do it yourself. From here to you have to come here, okay. If you find any difficulty, because it's very simple log equation, mathematical, you have to take log here, and then you have to make it, simplify it. 1 by n, it's come here, and then log a. There is a log formula. Log a by log b equal to log a plus log b, and so on. You can simplify it. So we would have this equation: p equal to 1 by n log k minus log q. And we can go continuation here. For the special case, when q equal to 1, then we can define p not equal to 1 by n log k here actually. If q equal to 1, so log 1 equal to, the 0. So in that case, we can define phi as a standard condition, phi e not equal to 1 by n log k. Okay, phi e not equal to 1 by n log k. Okay, so again from equation 14, if we go here, we can find this is actually here. Here P equal to 1 by n log k. Here we can rearrange this thing. P equal to P naught minus 1 by n log q. Here I am again saying you try to do, because due to the presentation, maybe it's a little bit confusing to you how could it come sequence. You can do it yourself. If there is any problem, then you can share me your email, then I will help you to correct it. Okay, how could it come? It's a simple equations. Okay, that's mathematical thing. Okay, P equal to P naught minus 1 by n log Q. From the relation, this is the actual relation, is actually, this thing gives free energy. Delta G naught equal to minus RT ln K. Okay, again we have this actually delta G naught equal to minus NFE dot. Okay, it's from electrical, Faraday constant and so on. F actually Faraday constant. So here we can make ln k equal to is actual conversion factor. Ln we can convert ln to log 2.3 log k. Okay, equal to delta G naught divided by RT. Okay, we can put this value here, and here we can have is P naught equal to F E naught divided by 2.3 RT. Again, if we put all the value, we can have, I think you know this, R is the molar gas constant, T is the absolute temperature, and F is the Faraday constant. Faraday constant value equal to is around 96500 coulomb. So if we put all this stuff, then we have P E naught equal to E naught, here E naught, we know all this stuff in a standard condition, divided by 0.0591 at 25 degrees Celsius. This is the equation, okay? If you, again I am saying, if you have any problem of doing this, you have to write me. Okay. Here you can find it. The values of P are defined in terms of the following half reaction, for which P naught is defined as exactly 0. As you know, the reduction of this hydrogen ion. Here you can see as conventionally P naught value is taken as 0. Is similar to the a pH value for the non-ionic, zero ionic state water, pure water, the pH equal to 7. You know that pH equal to 7. This is same conventionally, this is taken, this reduction potential P not equal to 0. Okay. When that means when hydrogen ion, here this is a standard condition. Here you can see P not, this actually means a standard condition here. When hydrogen ion at unit activity, activities unit is in equilibrium with hydrogen gas. At 1 atmospheric pressure, the activity of the electron, okay, in this media is equal to exactly 1. Okay, in that case, P not equal to, you can see, is equal to 0. Okay, because you know that P not is the minus log of electron activities. It's 0, log 1 equal to 0, P not is 0. Okay, fine. It just give an idea. This come is taken conventionally 0 P not. Considering the hydrogen ion at unit activity and is in equilibrium with hydrogen gas at 1 atmospheric pressure, and the activity of electron in that media is exactly 1, and in that case P not equal to 0. Well, fine, just for analogy, because it's for remembering is important. In pure water, you know that pH value equal to 7 and P value is equal to 5.9. Okay. High PE means is oxidizing environment. Low PE means is reducing environment. And high pH means is a basic media. Is high pH actually I mean that is greater than higher than 7. And low pH you know that it means acidic. Okay, but low pH is reducing, and high pH means oxidizing. And because next when I talk about we only say oxidizing or only high pH value. That means you have to know that this media is oxidizing media. When we say low pH, then is a this media is a reducing. Okay, even if consider the body, water body, if we consider is oxidizing, that means it's a high pH value. Okay, electrons are sufficiently available in the reducing condition. Okay, in reducing condition, in terms of electrons, if you consider the electrons, in a reducing condition, electrons are sufficiently available. But by contrast, oxidizing condition, electrons are wholly available. Okay. When we say thermodynamic equilibrium means no net flux of ions or electrons. Okay, thermodynamic equilibrium means no net flux of ions or so on. Okay, just have an idea or analogy. Okay, because here are a lot of equations here, so we can stop here. If you have any questions, you can ask me regarding the derivation of equation of P because it's very important. Okay, back to you, back to the students. You can ask me if you have any questions or you have any difficulty of deriving these P equations. হ্যালো, তোমাদের কোনো এনকোয়ারি আছে, কোয়েশ্চেন আছে? Okay, if you don't have any questions or any query, then you can stop here. But you can try yourself to derive these equations. It's important. Okay. In next lecture, we will talk about the Nernst equation. Is another equation, Nernst equations. Okay. So time to say goodbye now.
Assalamu alaikum, sir.
Walaikum salam. Walaikum salam.
Assalamualaikum sir. Assalamualaikum sir.
Walaikum salam. Walaikum